Okay, so for number 2 here, this is hopefully a straightforward conversion problem between, remember we've talked about all vectors have two name tags. One is the component form, and another way to describe the vector is its magnitude direction form, or sometimes we call this polar form as well. And you'll see shortly why the name polar form is also given to this, shortly meaning in the next unit. So here, let's just sketch out this vector. We want to find the component form of this vector that's got magnitude, or length 27, and a unit circle directional angle of 215. So first of all, let's find the angle here. We got to go 215, that's 180, plus another bit here. And so it's 215, 215 degrees all the way around, and then I'm going to go ahead and sketch in the length, or the length of that vector, and we know that it's 27. So I'd say there's actually two approaches to this problem. One is I'm just going to call it the right triangle trig approach, which is, you know that this creates a right triangle here, and we just need to solve this right triangle. And so to do that, we need to figure out this piece of the angle here. Well, we know that this top half of the unit circle is 180 degrees, so the difference between 215 and 180 is 35 degrees. So that little angle there is 35, and then we can just go ahead and use some straightforward right triangle trig. The length of this side here, since it's the opposite angle, we're going to use the sine function. So sine of 35 degrees is going to be, we'll call this, that distance y over 27. We solve that. 35 degrees is going to give us, it's going to give us 15.5. That's the length of this. Now, when we're thinking about the components, so you have to use your brain here to understand, or to realize that this is really going to 15.5 units in the down direction. So we have to think of this as going to be a negative 15.5 when we write the component form. And then to get this piece of the triangle, you're just going to apply cosine. So cosine of 35 degrees equals x over 27. X will be 27 cos 35 degrees. That also is going to be a positive 22.1. But again, we need to think about what we're doing here. This is a vector that's going to the left, so that's going to be a negative in both directions. So if you just blindly apply the formulas here, you might get yourself into trouble. So that vector would be negative 22.1, negative 15.5. And that would be the component form of the vector. The reason I said there was two different methods is you could also think about a unit circle approach here, which is what I have in that conversion toolkit set of notes that I passed out. And I like that one because you don't even have to think. You can just go on autopilot, since we are, for example, if you take the sine and cosine of the full 215, you'll get the sines right. So what we're really doing is trying to find like a coordinate on the unit circle here and then stretch it out by 27. So the foolproof way to do this would be say that the y1, the y coordinate is going to be 27 and just sine of 215 degrees, because that would give us the coordinate in this third quadrant here of the unit circle. And then if we plug that in, you'll directly get negative 15.5. And then x1 would be the cosine of that angle, the full unit circle angle, and that would get us negative 22.1. So you get the same answer. One's a little more foolproof. One relies on right triangle trig ideas. One relies more on unit circle ideas. But either one works here. Okay, the next problem is just a add two vectors type of problem. We're saying there's two forces pulling on an object. We want to find the magnitude and direction of the resultant force. So I've pre-sketched out a diagram here. Let's take a look at what's going on. So this first force I've drawn here is F1. And so its length here is 10, and its angle that it's making with the x-axis is 135 degrees. The second force I've drawn here is F2. It's making an angle of negative 110, so that's what this is here, negative 110, and its length is 20. So we want to add these two vectors. Right now, remember, when we add vectors, they cannot be, you have to put them head to tail, so my diagram here is not really set up for an add type problem, so I'm going to go ahead and just slide this up here, put it head to tail, and just to kind of see what's going on, I'm going to move that angle there because that'll help us solve for some angles later. And recall now that the resultant is the sum of the two vectors, and we want to start from there, go to there. And so it's really the magnitude and direction of this green vector that we're trying to find. So one approach to do this would be just to solve it using law of cosines. That's why I said challenge yourself doing it two ways, using trigonometry. So this one's already set up to hopefully kind of do it with trigonometry. We have that this side here is 10, this side of this triangle is 20. So to see what's going on here with the angles, I think it might be, when I slid this unit circle angle over here, I'm going to attempt to draw here anyway, a straight line going across. So we can see where this negative 110 is going towards. So remember, law of cosines would really help us out here because we can find the length of this if we have side, angle, side. So we have the two sides. What I'm trying to do here is can we determine what this angle here is between the black and the red. Well, we know from this horizontal line, it's a full 110 degrees. So we'd want to subtract this angle if we could find it. Well, one way to do that in this problem is, remember alternate interior angles here. This angle here is going to be 45 degrees because 135 plus 45 is the full 180. So this piece up here then, alternate interior angles are congruent. That would be 45 as well. So this angle here has to be 110 minus 45 degrees, which would be 65 degrees. So that would be that angle here. So armed with that information, you could use the law of cosines to knock out the length of this vector. If we called it, I guess we'll call it just r, the length of vector r. I'm not going to go ahead and fully solve this, but we'll go ahead and set it up. So the side across from the angle squared is going to be 10 squared plus 20 squared minus 2 times side times the cosine of the angle between them, which in this case is 65 degrees. And you could use this to find r, the length of this, and then you can go ahead and use law of sines to find these remaining angles to figure out what direction this thing is actually going. Approach 2 is, if you recall, one of the reasons we like to work with component form is it makes vector addition and other vector operations much easier to accomplish. And so that would be the other idea here is let's go to a paradigm where we just convert them to component form. So if we go ahead and do that, we need to rewrite F1 in component form. And based on that conversion problem we just did, we know that the x-coordinate or the x component of this vector is just simply going to be 10 cosine 135. And then the y component is going to be 10 sine of 135. F2 similarly is just going to be 20 cosine of negative 110. So I'm using that unit circle idea here when I'm converting from polar form or direction magnitude form to component form. This is 20 sine of negative 110. And so essentially what we're going to do is we're going to add those pieces here to get F1 plus F2. I'm not going to do the calculation here. You're going to add 10 cos 135, 20 cos negative 110. If you did that, when you punch that in your calculator, you'll get negative 1391 Same thing here. If I add these two components, I would get negative 1173. Sorry, 1173. And this looks like it's pointing to the third quadrant, which actually makes sense with our sketch here. So we have some confidence that it's going 13.91 to the left, 11.73 down. That looks like what's going on here. And so from here, this problem's asking to find the magnitude and direction. So we'd have to go through the process of converting back to this form. So we put it in this form, the component form, to go ahead and to add them. But now we'd have to convert this back. So we could draw a little sketch here. And we know that this side here is 1173. This side here is 1391. You could use the Pythagorean theorem to get the length here. So the length of r is going to be square root of 11.73 squared plus 13.91 squared, which you crunch that through, you get 18.2. And then the direction angle, we're trying to find this right here. Well, we could find this piece right here using tangent. So tan of, I'll call this little piece here maybe alpha. So tan of alpha is just going to be opposite over adjacent. So SOHCAHTOA, 1173 over 1391. And if you solve that, you get alpha equals 40.1 degrees. But since we need to add, and then we need to add 180 here because we're pointing in this third quadrant. So I'm going to go ahead and add the 180, and you would get alpha equals 220.1 degrees. And if you use the same ideas here with this law of cosines, you should get the same answer. So these are equivalent, just different ways of getting at the same thing. Okay, so here, moving on to number 4, we have a quadrilateral A, B, I'm just drawing this randomly here, C, and D. And what this is saying is that we have, they're non-collinear, which I've drawn here, and it's saying that vector AB, so if I draw this, that's the vector from A to B, plus CD, so the vector from C to D, needs to be the 0 vector. Which means that if I add these two things, like if I somehow can move that vector over here, I need to end up where I started. So you can see in this particular one that I've drawn, that's not happening because AB plus CD, I put them head to tail. I need to end up where I started. Well, so how can that happen? How do I need to change the orientation of C and D for that to happen? Well, they certainly need to be the same length. So that would be the first set of reasoning in order to end up where I'm starting. So the length of AB and CD need to be the same. So here I'm trying to draw an A, B, and CD that are the same length. So now I have them the same length, and let's see, can this particular one, can AB plus CD equals 0. Now it's not letting me move CD by itself. But you can see if I slide this over to be head to tail, I still don't end up where I started. So they also need to be in the same direction. So this quadrilateral needs to have these opposite sides that are parallel and in the same direction. And then it doesn't take long to conclude that really, so if I have an orientation like this, the only way that that's ever going to happen is with a parallelogram. So in this case now I can see that if I travel from A to B, and if I had a vector where I can go back CD, I need to come back to where I started. So parallelogram is the answer for this one.